Hi all, can you please send me a chat message so I know you can hear me? All right, cool. Looks like we got everyone. So let's uh, let's try this. This is our last day on material about polarization. So uh, this is going to be somewhat more mathematical than the past two classes because we're going to talk about how we can represent polarization with matrices. We started talking about that using these things called Jones vectors before spring break. But now we want to see how we could take all these devices that change polarization and represent them with matrices. It kind of cleans up a lot of the mathematics because then we don't have to keep carrying around phase factors and such. So it's a nice way to look at polarization. Give me 1 second here, I'll grab the textbook, and I'm just going to let you guys know this section. So all of this material is from chapter 8, and it's 8.13. So that's kind of what we're covering today. The book covers these two different ways to represent polarization. Jones matrices, which we're going to do, and then these others called Muller matrices, which we're not going to have time to cover this semester. But if you read about that and you have any questions about that approach, which is equivalent and has some benefits, though the matrices are more complicated, I'm happy to talk about it in office hours. So, all right, here we go. So, basically, just kind of reviewing what we started with before spring break, we could represent the polarization, a polarized light wave, as a column vector. So as you guys can see here, our column vector, called a Jones vector, had two components. The top was the X polarization, and the bottom component was the amplitude of the Y polarization component. So these are the X and Y components of our electric field on our axes. When we have devices like polarizers or wave plates, so on and so forth, basically what they do algebraically is they block certain components or they take components and rotate them. So more or less, we can think about devices like polarizers or wave plates or chiral materials as basically doing mathematically a linear transformation. The zeros are our electric field components before we hit whatever device we're talking about. And the components with the subscript 1 are the electric field components after we pass through that device. So as our kind of the simplest example here would be an X polarizer. So we could kind of take this system of equations and write it as a matrix equation. That's what's showing down here. Sorry, things froze there for a second. So here we have the electric field after our polarizer, the electric field before our polarizer, and our polarizer is represented by a matrix. For an X polarizer, it's going to be a matrix with 1, 0, 0, 0, so that when we multiply it, the polarization we get out at the other end, E1X is unchanged. It's the same as it was before. And the Y component of the electric field afterwards is completely blocked. So that's transformed to a 0. So this is the basic idea, is that we represent our polarization as column vectors, and then the different types of devices can be represented mathematically as a matrix. if we block a certain component or block a certain polarization, we build the matrix such that it makes that component 0. If we rotate a polarization, then we might need to build a matrix such that we take this y component and, for instance, add it to the x component. This can work with like a variety of different things. So if we look at our matrix for a y polarizer, it'll be similar, but there'll be a 1 in the lower diagonal corner instead of the upper diagonal. For a half wave plate, we have to take the y component and add a phase of pi. So essentially, we need to slow it down relative to the x component. And we can do that with a matrix like this. We don't change the x component at all, but we slow down the wave by half of a cycle, meaning we turn a crest into a trough for the y component. So this minus sign here does that for us. When we take this matrix and multiply it by, let's say, a light wave polarized at 45 degrees here, so we have equal x and y components, then we slow down the y component compared to the x component. And so then we would have a light wave polarized not at 45 degrees, but at minus 45 degrees due to the negative sign here on the y component of the electric field. That'll do the same thing. You'll notice it'll do the same thing in reverse as well. If we take a light wave polarized at minus 45 degrees, then this same half wave plate would then convert it back to what we started with. A light wave polarized at positive 45 degrees. For a quarter wave plate, remember that converts linearly polarized light to circularly polarized. So we need to add a phase shift between the x and y components of pi over 2. So that works out to basically multiplying the y component by a plus or minus I, depending on whether we want right or left circular polarized light. So a matrix like this would do that. So if we take our light wave focused at, or light wave polarized at positive 45 degrees, remember wave plates only work if our light wave is polarized at 45 degrees, our incident light wave. We multiply by this matrix, 1 times 1 will give us an x component that's unchanged. And then we add to that 0 times 1, which is 0. Our ending y component would then be 0 plus or minus I. So it adds in that phase shift of I into our lower component. Does this, is this making sense to everyone? We're basically kind of rewriting the stuff, how we know these devices work, but we're trying to build 2x2 matrices that model that effect mathematically. Are there any questions so far? Any points of confusion or questions on how these matrices are built? Okay, if not, it's worth just like making sure, kind of going through all these matrices and making sure the properties we expect them to have, that they do work like that. So we've checked like a few of these things, that the Y polarizer does block the X component of an incident polarized light wave. A half wave plate does add the negative sign we need onto one of the components. And this quarter wave plate matrix puts the plus or minus I in the place where we need it. Other things we could check, for instance, is that this idea that we need to have a light wave polarized at 45 degrees relative to the axis of a wave plate for it to work. So for instance here, if we just send in an X or a perfectly X polarized or perfectly Y polarized light wave, and we send it through a half wave plate, ideally, then if we multiply by this matrix, it shouldn't change anything at all. Wave plates only work if we have 45-degree polarization. So we could check that here and see, multiplying out this matrix for the half wave plate. So 1 times 1 gives us a 1 plus 0, and the bottom components give us 0. So the polarization vector, the Jones vector, is not changed at all. And we could show that this works for the Y component as well. So the same properties that our devices have, the matrices have as well. Wave plates only work with an initial beam that's polarized at 45 degrees. If you try to put in a light beam that's polarized completely along the X direction or Y direction, it will do nothing, just like an actual wave plate device. So another thing we might want to do is model, well, we rotate these polarizers. We could have a polarizer at a certain angle. And if we want to rotate or change that angle, how do we have to change the matrix? So that's a good question to answer. So we could kind of take a look at it and take some information from linear algebra. And there are these things called rotation matrices that basically do the effect, cover the effect of rotating for you. So if you want to, if our goal is to rotate some kind of matrix, if we're rotating a column vector by an angle theta, we have to multiply that column vector by this rotation matrix. So this is just a mathematical result from linear algebra. If we wanted to model the effect of rotation on a matrix rather than a column vector, we have to do something like this. And you guys could just kind of copy down the last line here. This middle stuff is really going through a linear algebra proof. But if you want to model the effect of rotating a matrix by an angle theta, you have to multiply on both sides of the matrix by this rotation matrix. On the left, you multiply by the rotation matrix itself. And on the right, you multiply by the inverse of that rotation matrix. So what we can do, if we wanted to take a polarizer that's, for instance, an X polarizer, and then rotate it 45 degrees so it becomes a 45-degree polarizer, what we have to do mathematically to get the correct matrix is take our X polarizer matrix and plug it in here for A, and then multiply through on each side by the rotation matrix and its inverse. So let's see, since this is like a general mathematical property for all matrices, this will work here as well. So let's see how this works. Let's take our X polarizer matrix, plug it in here for A, and multiply through by these rotation matrices to get our polarizer oriented at an angle theta. That will be the matrix A prime here. So writing this out explicitly, here's our X polarizer matrix. This is our rotation matrix here for the rotating the object by an angle theta. And this is the inverse of that matrix. I'll leave this to you guys to check this, that this matrix and this matrix are indeed inverses. But if you multiply these two together, you'll get the identity matrix. So let's see, going from, we have to be careful on rotating these by the, or multiplying these in the right order. So we'll do this matrix and this matrix first. So 1 times cosine theta plus 0 times sine theta. That will give us cosine theta in the first term. The second term, do this in blue. So we can go kind of just multiply through by the rules of matrix, the rules of matrix multiplication. So if you want the bottom term here, you're going to get 0 times 0 here. That'll give us a 0, so on and so forth. Let me reset this slide and just kind of give you the result here when you go through each one of these terms. So multiplying these two matrices gives you this guy. Then we have to multiply these two together. You should see that multiplying through, for the first term, we're going to have a cosine squared minus 0. For the second term, we're going to have cosine times sine minus 0, and sine times cosine minus 0. And then we should have a sine squared in the last term. So our total overall rotated polarizer matrix for a polarizer rotated by an angle theta looks like this. The diagonals are cosine squared and sine squared, and the off diagonal elements are cosine theta, sine theta, cosine theta, sine theta. So for instance, if we plug in some numbers here, let's say we rotate our polarizer by 45 degrees, so it's polarizing along the 45-degree axis. The matrix that would model that effect when multiplying by a Jones vector would look like this. 1/2 in every element. If you wanted to rotate the polarizer by like 60 degrees, you just have to plug in 60 for theta. So this is a general result for really any polarizer. You could also do a small angle approximation here. If you're rotating by a small angle epsilon, the matrix reduces to the form like this. So if you're just like within 1 degree or less from off the polarizer axis is rotated 1 degree or less from the x-axis, this is a reasonably good approximation. At some point, probably you guys have done matrix multiplication before. If you're still in linear algebra or you're just taking it, you may or may not have done rotation matrices yet, but you'll cover them at some point in that class, I would think. But here you're going to have to thing you have to take for granted then for this class is that to model the rotation on a matrix, you have to go through this rule here. So if you haven't done that in linear algebra yet, or you haven't taken that course, take this on faith, but hopefully the algebra you guys have done before. Any questions at this point? All right. So what I'm going to do for your homework here, for the problem I'm going to give you on this material, what I'm going to do is kind of have you guys analyze, like work through some of this matrix math. But for what will make it useful is if you have some of the basic matrices for the different types of components written down. So I'll have these on the slides for you, and these slides are already posted right at the top of the Canvas page. So for the a polarizer with that polarizes along the x direction is this matrix. Y polarizer is this matrix. And from the last slide, the polarizing at positive 45 degrees would be this matrix. I'm just factoring out the 1/2 here. So factoring out 1/2 from every term. If we do the same analysis with minus 45 degrees on the last slide, we would get this matrix here. Thing that changes are the off-diagonal elements get that negative sign. We already have our quarter wave plate matrices. So for left-handed, circularly polarized, a quarter wave plate that converts to left-handed circularly polarized light, we have a minus I in the lower corner element. For a quarter wave plate that converts from linear to right circularly polarized light, we have a positive I. And then we have these other things which are going to be called right circular polarizers versus left circular polarizers. So they also convert from linear to circularly polarized light, but they do it in a different way than quarter wave plates. Quarter wave plates modify one of the polarization components and add a phase to give you an overall effect of circularly polarized light. Whereas polarizers give you circularly polarized light by blocking one of the components. So this guy here, the right circular polarizer, this matrix is different from this guy in that it models the left circular component of the incident light wave being completely blocked. So for this guy here, you don't really, or theoretically anyway, you don't lose any power or strength of your electric field in your light wave going through this device. For this guy here, you do. You lose about 1/2 of your total electric field strength. So that's kind of how this guy here is different from this guy here. And that's what this 1/2 models. Similarly with the left circular polarized, we're totally blocking one of the components to give us circularly polarized light. Whereas here with the quarter wave plate, we're changing the phase on one of the components and we don't lose as much power. That's why the matrices are different. The end result though will be circularly polarized light, but the overall magnitude would be different, which is what these 1/2s are modeling. In your homework, in your problem for this set, you're going to be working with some of these matrices. So any questions at this point?
Does the 1/2 on the plus and minus 45 degree polarizer on the left work the same way as the polarizers on the right, or does this only apply to the ones on the right?
So you're asking, just correct me if I'm wrong here, but your question is, does the 1/2 over here do the same thing as the 1/2 over here?
Yes.
Yeah, that's a good question. Let me reset the colors on the slide for a second. Bring everything up. So the short answer is yes. The reason this 1/2 appears is because with polarizers, as opposed to wave plates, you're always losing some electric field rather than inducing a phase. So you'll see, even with these polarizers, even with the X and Y polarizers, if you work out the total electric field strength on one side and the other, it will be weaker for anything called a polarizer. It's apparent in the circular polarizers and in the 45-degree polarizers with this 1/2. But the same effect is kind of hidden in here. You just don't see it. Instead, the presence of this 0, the fact that one component is completely blocked, lowers your field strength. So the short answer to your question, Jacob, is that yes, with every polarizer, you're always seeing a change in total magnitude of the electric field. With a wave plate, theoretically at least, you're not. Of course, in the lab and stuff, you're going to have, wave plates are made out of things, so some of the light's going to reflect rather than transmit through. So experimentally with wave plates, you lose some field strength too, but with a polarizer, it's theoretically, polarizers theoretically must lower your electric field strength. That's a good question. Any other questions? Okay, then let me just see here. The last thing that might be useful is, of course, on Wednesday we talked about chiral media that rotate the polarization of light slowly as you pass through due to inducing a phase difference, or due to inducing, we have different indices of refraction for right and left circularly polarized components. So it rotates the overall linear polarization by an angle delta phi. So this type of device, so a Faraday effect isolator like we talked about on Wednesday, the Jones matrix for this type of device is just a rotation matrix. So you could take the rotation matrix from 2 slides back and just, instead of the angle theta, use the angle delta phi. So if you want to model a, for instance, a Faraday rotation device that rotates by an angle of 30 degrees, just put in 30 degrees for delta phi here and multiply by the column vector for your initial polarization, and you'll get out your final polarization. I find that, like, overall, most physics majors, you guys have done a lot of matrix multiplication at this point. I find that this is, in some ways, it's a little more tedious having to carry around all these matrices. But the benefit of this approach is that you don't really have to think about phase differences or indices of refraction differences as much. And the type of notation and things you have to carry around from line to line becomes a bit simpler. So when dealing with polarization or working through a problem with polarization, this type of notation really helps. The only tricky things is that, let's say we had more than one polarizer or more than one device. So we have an initial polarization, let's call it, well, that's E naught. Might be right circular, might be X polarized, might be Y polarized, whatever it is. And it could hit multiple different devices in an experiment or some situation we're considering. Perhaps this is an X polarizer. Perhaps this is a wave plate. Perhaps this is a Faraday rotator. If we want to model the effect of all of these things on the light wave and see what happens to the polarization at the end, well, we just have to chain our matrix multiplication. So the only trick here is that because matrices don't commute, we have to make sure we multiply by the matrices in the correct order. So in order to get the correct output polarization, you start with your input polarization, Jones vector, and then you multiply on the right by the matrices in the order the light hits the devices. So we hit A1 first, so that's the first matrix we multiply by. Then we hit device A2 first, so that's the second one. Then we hit device A3. So in effect, the order in which you hit devices, you have to multiply by the matrices in the reverse order. So you multiply on the left always by these matrices. So if you're building a whole polarization sensitive experiment with lots of devices, theoretically anyway, you can determine the overall effect on the polarization of your laser beam or your light source by figuring out what the matrix for each of your devices is and working out all the matrix arithmetic. This approach is generally best if you're trying to predict the outcome or determine the outcome of an experiment or design a device that outputs a specific polarization. This matrix mathematics is much easier to kind of code up because you can obviously build arrays and matrices and do matrix multiplication quickly if you could write some computer code to do it. So that's the other benefit of this approach. The only kind of, oh, okay, sorry, one more thing before we finish. As another example, we just might want to check what happens, for instance, do we get the right physical properties when we chain devices together? So the simple case might be to look at cross polarizers. Remember, if we had an initial light source with some arbitrary polarization, E naught, if we send the light through an X polarizer and then a Y polarizer without changing anything, it should block all of the light. So we should get zero, a magnitude of 0 for our X component polarization and our Y component polarization. And indeed, if you multiply these two matrices together, you get the 0 matrix. So no matter what initial polarization you start with, you're going to get 0 out on the other side. So these matrices model the effect of our cross polarizers working really well. And indeed, we could think of that experiment that we did where we put the third polarizer in between the two cross polarizers and it started letting light through. That could be modeled by taking, like, for instance, a 45-degree polarizer matrix and putting it in between here and then multiplying it out. You'll see that that changes this overall matrix and some light will start getting through because some of these components will not be 0. If you want to have a little bit of extra practice with this stuff, that's a good problem to work through. The other thing you could do is look at what happens if we rotate one of our polarizers. So if we take our X polarizer here and rotate it by a small angle, we should see in our matrix that some light starts getting through, that the components of our output polarization are no longer all 0. So we can use our kind of like small angle. So we take the X polarized matrix and replace it with a matrix or a polarizer rotated a small angle epsilon from the x-axis. We multiply this through now, all of a sudden, our total overall Jones matrix no longer will make the output polarization 0. If we multiply these matrices through, the rotated first polarizer and the non-rotated Y polarizer, the overall matrix is this with the small rotation angle in the lower left. Multiply this through by our initial arbitrary X and Y polarization components of our initial light beam. And we see we do get some polarization out. The second polarizer is a Y polarizer, so what we get out is a little bit of the Y polarization. It's still going to be polarized along the Y direction, but now the polarizers aren't perfectly crossed, aren't perfectly at 90 degrees, so we get some small amount of electric field through. So just a little bit of practice with these matrix mathematics and kind of showing that the properties of our devices are well represented by these matrices. So interesting thing here is you can use this to basically predict the output irradiance or intensity. So basically proportional to electric field total electric field output squared. So the output is about angle squared times the input. But if we go back to our last lab, we'll note that this is more or less I out basically I in times cosine squared of theta. So what we're really seeing here is a kind of approximation of Malice's law. So another confirmation that this matrix approach to treating polarization is working. Lastly, the only real limitation to this approach is it doesn't really handle unpolarized light as well. So if you remember unpolarized light, we can kind of think about it as light where the X and Y polarization components are varying randomly, like they have random phase differences, random phases compared to each other. If we wanted to write the Jones vector for this type of light source, it would look something like this. In practice, this is something that's changing very quickly. So we can't really treat unpolarized light with the Jones vector and Jones matrix approach. If you're doing an experiment where your light always has some definite polarization, this works really well. But if it's unpolarized at any point, the Jones matrices approach doesn't work then. The other approach, which I'm not going to cover in class, but I encourage you guys to read about it, and I'll have some slides if you're interested in that following up from here, is the Muller matrix approach. That is a different way to build matrices to model polarization, but also it's able to handle unpolarized light. But as far as problems are concerned, we're not going to be doing that. So only read it if you're interested, really. As for the homework problem on this material, that will be this one here. So there's going to be 3 parts. Basically one on, first part's on Jones vectors. So basically you have to work and simplify, you know, what different polarization states these are and how you know that. The second one, I give you the matrix for a circular polarizer minus the 1/2, so it's not normalized correctly. But what you can do is show for this part of the problem, confirm that it does indeed block or a left circularly polarized light source. So you could have to multiply by the Jones vector for left circular light and show that you get 0 on the other side. I guess I don't really tell you one way or the other which one it is, but you have to show that it blocks one of them. And the last part is another question about polarization state, analyzing the matrix. So that's what you're going to have to do for working with this material on the next problem set. That being said, that's the last of the new material for today. So I'm here for questions. So Christine, you raised your hand.
Will these questions be posted on Canvas, or will we just need to have to go through the slides?
Would you guys? I'm planning on putting an assignment on Canvas for submitting it, but I was hoping you guys could just use the questions from the slides.
Okay.
And then I figured putting them in the slides would make it easier for you guys to know what material the question related to, because that's one of the things that's harder to do when we're working remotely. So I was hoping, if it's not a problem, I was hoping you guys could read them from the slides. The slides are posted to the top of the Canvas syllabus page under the announcements section. And I'll do that for all the slides moving forward. If this presents a problem for reading the problems, send me an email. Any other questions?
Yeah, are they all, can you hear me?
Yeah.
Okay. Are they all going to be contained within this PowerPoint? So like we'll only have to go into one PowerPoint to find the questions?
So all for April 3rd, all of the questions are in this one PowerPoint. So for instance, I'm the wrong way. There's basically at the end of each class, so you'll see problem 2 was at the end of our class on Wednesday.
Okay.
And then for the slides at the end of our class for the question at the end of our class on Monday was this question.
Okay.
So there's one question for each class, really.
Sounds good.
I'm going to try to stick with that for the remainder of the lectures. I might probably be 3 or 4 questions a week, but. So going back to where we are here. Yeah, so this will be our question for this week. I've also included, for those of you interested, some slides on Stokes parameters and molar matrices, which are the different types of matrices that allow you to model unpolarized light. If you're interested in it, those slides might help as you go along with the reading. But we're not covering that in class. Next week in class, we're going to move on to more matrix approach stuff, but how modeling like lenses and lens systems with matrices. So it's what I really call advanced geometrical optics. Okay, any other questions? Okay, if not, then we're done with new material for today. I'll hang out for a bit if people want to discuss homework or have questions otherwise, but otherwise we're done with material and you can feel free to leave. Have a good weekend. I'll talk to you guys on Monday.
Have a good weekend.
Yep, you too.
I have a question.
Yeah.
Wait, can you hear me?
Yeah.
In the last slide, when you had the matrices 0, 1, 2 slides ago, yeah, how did you get epsilon E? Can you like do the math out?
For which part? The last one here?
The part before the last one. So like.
So here.
Yeah.
Sure. So 0 times 1 is 0. 0 times epsilon.
Oh, okay.
And then if we do the second component here should be 0 times epsilon is 0. I'm sorry. Oops. Screwing up my math here. 0 times epsilon is 0, plus 0 times 0 is also 0.
Mm-hmm.
Then for the third term, 0 times 1 is 0, plus 1 times epsilon is epsilon.
Thank you. I was just confused because I was like, wait, 0 times epsilon is 0.
Yeah, remember it's for the first row, it's first row times first column gives you the first element. First row times second column gives you the second element. Second row times first column gives you the third element, so on and so forth.
Yes.
Luckily, all these matrices are
Thank you.
So.
Thank
Okay.
you.
Yep.
Have a nice weekend.
You too.